ABC Listen. Podcasts, radio, news, music and more.
When you visit the archaeological site Pompeii beneath Mount Vesuvius, just outside the city of Naples, one of the most powerful things to see is the casts of victims who died when the volcano erupted there in the year 79 CE. And most poignant of those casts is of a couple reaching out toward one another, caught in the very moment that the lava, ash and gases consumed them. Today, around 10% of people live within 100 kilometres of an active volcano. Thankfully, modern volcanologists, volcano scientists, have a much better understanding than the residents of ancient Pompeii of how volcanoes work and their likelihood of eruption. Associate Professor Teresa Ubide is one of these volcanologists, now based at the University of Queensland. As a 10-year-old schoolgirl in northern Spain, Teresa's imagination was opened up to what she calls the guts of a volcano, and she's travelled the world visiting volcanoes and analysing their future-telling crystal balls. Hi, Teresa.
Hello.
Volcanologist has to be the coolest job description in the world. Where does the term come from, volcanologist?
So volcano comes from the Roman god of fire, Vulcan. And so it really reflects how humans have always been fascinated by volcanoes, which generate very good resources, but also can cause major problems like hazards or impacts to the atmosphere.
I guess it's something that people would have always been so aware of in their landscape. There would have been, stories and songs and prayers around these things that would have such powerful effects on the landscape and would have been so mysterious at the same time.
That's right. So volcanoes are fascinating and very useful because they create beautiful landscapes and fertile soils. So they have attracted humanity for a very long time. But as much as they have attracted it, they have also posed natural hazards. And that's why we need to be as ready as we can for volcanic eruptions.
You live in Australia now, but as your lovely accent suggests, you didn't grow up here. Where did you grow up, Teresa?
So I'm from Spain, San Sebastián, which is actually very popular amongst Australians.
What's it look like for people who haven't been lucky enough to go there?
Oh, it's so beautiful. It's a little city by the sea, and it has a lot of French influence. It's by the border with France. It's only half an hour drive to France. And so it looks a bit like a mini Paris with amazing food and, beautiful sea and mountain. It just has everything.
What kind of food do you miss most living in Australia and not being able to just pop down to your local restaurant in San Sebastián?
I guess the pinchos. So these are the mini tapas that are typical of the region I'm from, and they are pieces of art. They just build beautifully and they are so tasty and it's so relaxing to go with your family or your friends to have a pincho with a drink and then you go for lunch.
So you say this part of Spain is mountainous, but is it mountainous in terms of volcanoes? Are there volcanoes in mainland Spain?
There are some volcanoes in mainland Spain, but they're not in the region I'm from. And the most famous volcanoes in Spain are actually in the Canary Islands, which are in the Atlantic Ocean. And they are generated by a heat anomaly inside the Earth that generates this kind of line of volcanoes at the surface in a similar fashion to Hawaiian volcanoes or the volcanoes in Eastern Australia, which are mostly extinct at the moment. But you may have heard of some of them, like the Glasshouse Mountains, for example, in Queensland.
So growing up then, you weren't next door to volcanoes. How did you first get interested in studying them?
Oh, yeah, I was in my first ever class of geology at school, and I didn't even know what geology meant. It meant the study of the Earth, but I only took it because it was geology and biology, and I liked biology. Anyway, day one of the course, and the teacher said, "Oh, can you all please take your notebooks out and draw a volcano?" And so we did. So I drew, and my other classmates drew a triangle and some lava coming out of this triangle on the notebook. And then after a couple of minutes, she did the same on the blackboard. So she drew the triangle with lava coming out of it. And so she said, so everyone has drawn something like this. And what you have not thought about, because you don't know about it yet, is that what comes to the surface, all this lava and ash that comes to the surface, is actually controlled by what happens inside the volcano. And so she then started to draw these conduits and magma chambers and reservoirs that were feeding the volcanic activity. And she started to explain how the dynamics of these inner reservoirs, the guts of the volcano, actually controlled what happened at the surface. She kind of like opened the volcano as if she was, dealing with a doll's house. And I just found that so fascinating. I was completely hooked.
It's so great because, as you say, that visual, that little symbol of a volcano, which we can all call to mind immediately, the triangle with the stuff at the top, the sense that beneath that is this whole universe so clearly grabbed your imagination at
That's
that
right.
point.
It's just like the volcano is just the tip of the iceberg. Yeah.
So did you have the thought there, this is something I'll study as I get older? Or how did you get the idea that, this is something I'm actually going to give my professional life over to?
I just really became fascinated by volcanoes, and I then learned that to do volcanology, you had to study geology. And so I did, and I remember having my insecurities just before going to uni, because I did like anything sciencey. So I remember telling my mum, in Spain, I don't know many jobs in geology. Should I really do something more, job ready, like engineering or something? And my mum said, you just do what you love and you will be fine. And I really appreciated that.
What about your dad? What was his view of you devoting yourself to volcanoes?
Well, he loved it because actually he would have loved to study geology. But when he went to uni, he had to study something in the city where he was from. He could not travel elsewhere. So there was no geology in the city he was from. So he did chemistry instead. And, that's how he met my mum.
But he got to live out his geology dreams through his daughter.
Yeah,
Perfect.
He had these books at home, and he was really excited.
As we were saying, Teresa, volcanoes have been around as long as there have been people on the earth, and so people have been trying to figure them out and predict them and understand them. It wasn't until the 1960s, though, that a geological theory kind of allowed a new scientific understanding of volcanoes. Can you explain to me plate tectonics and how it shifted, excuse the pun, how we understand volcanoes and what creates them?
Yes, so you don't get volcanoes just anywhere, geologically speaking. They are very much controlled by the inner workings of the Earth. So you may have heard that the Earth is built of different layers, as if it was an onion, a big onion. And so the outer layer is the crust, then you have the mantle, then you have the core. And the outer part of this mega onion, the crust and a bit of the mantle is actually split into different tectonic plates, and they move in different directions, and new tectonic plates can grow in the middle of the oceans, in mid-Atlantic ridges. And actually, those mid-Atlantic ridges where new ocean crust grows are the biggest volcano factory on Earth. They are where the majority of volcanoes occur, and they're just less obvious than the ones we see at the surface. So the majority of volcanoes are actually under the water, and because we don't see them, we are less aware of them. But that's a key area of volcano generation where tectonic plates move away from each other and new oceanic crust is being generated. That's the number one place. But then you also get volcanoes, and really explosive and hazardous ones, where tectonic plates move towards each other. And when that happens, the denser one goes underneath the other in a process called subduction. And so what happens then is that process of subduction of the denser tectonic plate under the other releases a flux to the upper plate, and that one then melts, and that generates molten rock, which is magma. And that, because it's buoyant, is less dense than the surrounding rocks, it moves towards the surface, and you get a line of volcanoes at the surface that follows that subducting plate at depth. And that's what you get in all of the Pacific Ring of Fire. So, for example, the western coast of South America is full of volcanoes, and also on our side, New Zealand, the Philippines, Tonga, and so forth.
So this understanding of tectonic plates, and obviously a crucial role they play in the creation of volcanoes, it really wasn't until so recent as the 1960s and 70s that geologists understood that that's how they operated.
So, of course, a new theory takes a lot of effort to put forward and prove, and, lots of geological evidence from lots of different points of view, particularly from the ocean. But also, in terms of volcanology, yes, you're right. Volcanoes are very much controlled by the plates, but there's also locations where volcanoes are not necessarily linked to tectonic plates. And that's what happens, for example, in Hawaii. So Hawaii is in the middle of a tectonic plate, the Pacific plate specifically. And it's there because there's a hot spot inside the Earth, a very hot area of the Earth that comes from very, very deep inside the Earth. And it's like a cooling mechanism from the Earth. And so what you get is a volcano at the surface. And because the Pacific plate is moving on top of that stationary hotspot that doesn't move, you get a line of volcanoes. And that's what you get at Hawaii.
So they're not only just where the plates meet, but can be at these particular hotspots.
Yes.
Well.
Another famous one is Iceland. So Iceland is in the mid-Atlantic ridge, is the only region where there's a lot of volcanism above the seawater level. And that's because there's extra magma coming out, because not only you have two tectonic plates moving apart, but also a hotspot in the same region. So there's extra magma coming out, and then you have so much magma that you make it all the way to the level of the seawater.
When you describe the Earth as being like a big onion, a giant onion with these different layers, how far down do we have to go before we get to this magma, before there's this sort of hot liquid? Is it very far down?
So the magma comes mostly from the Earth's mantle, below the crust. Depending on how thick the crust is, you may meet the mantle earlier or later. In the continental crust, the thickness typically is around 30 kilometers. So below 30 kilometers of continental crust, you meet the mantle. But unlike, contrary to most people's thinking, who think the mantle is some sort of pool of magma beneath our feet, the mantle is actually solid. But it can melt in certain circumstances. And those are where tectonic plates move apart, because that mantle is pushed up and the pressure drops and then it's able to melt. Or when there's tectonic plates moving towards each other, because you introduce a flux and that makes the mantle melt. Or when you have a hotspot, because the temperature is higher and you can also melt. Other than that, the mantle is solid. And that's why you only have volcanoes where there's molten rock. And that's controlled by the geology.
I feel safer somehow just knowing that, Teresa, that it's first of all, there's 30 kilometres and then it's still solid. It's only going to turn into that magma in certain other conditions. That has helped my feeling of safety on the planet. So you described how that first teacher, your first ever geology lesson, introduced this idea to you of a volcano being like a doll's house that you could open up and imagine what was going on inside it. So if we do that, if we take apart the front door of our volcano doll's house, what's inside that mountainous structure? What's going on?
So what happens as the magma that has been created tens of kilometers beneath the surface moves up towards the surface, it starts to cool down. And when it cools down, it starts to generate crystals. And as it does so, it keeps changing in chemical composition. And what it does also is that all of these things happen particularly where the magma stops. So it may have lots of stops on its way.
What's stopping it?
To the surface. So these stopping areas are where the magma reservoirs or magma chambers are generated. And they could be generated for different reasons. For example, if you have a change in the type of rocks that is on the way to the surface, that change in density of the rocks may make a very good area for a magma chamber to develop. It could also be that because you are rising up towards the surface, you start to lose the volatiles that were dissolved in the magma. So, for example, water, when the magma is very deep, is dissolved in the magma, but when the magma comes towards the surface, it starts to separate because the pressure drops, it exsolves. And so when that happens, the viscosity of that magma increases, and that might be an area where the magma also stalls and, makes this one of these stops where it makes a magma chamber or magma reservoir and starts to cool down, drop crystals, and change in composition. So when we draw the inside of a volcano, we cannot see it directly, but we can see it through our science. We normally draw a sequence of magma chambers and conduits that bring that magma from depth all the way to the surface. And so we want to know exactly what's the shape, at what depth those reservoirs are, what kind of interconnectivity they have between them, because this knowledge of how the volcano, the doll's house, looks inside is important for when we have unrest. And so when we measure, say, earthquakes or deformation of the ground by a few millimeters of centimeters. We know where these earthquakes and deformation come from at depth. And so if we know that's an area where the volcano typically stores magma, we can make interpretations on what may happen next.
When did you first witness an active volcano actually with your own eyes up close, with your scientist's brain, but with your human body and eyes? Where did you see your first active volcano?
So the first eruption I saw was at Mount Stromboli in Italy. So this is in the Mediterranean Sea, north of the big island of Sicily. There are a few smaller islands, and Stromboli is one of them, and it's really spectacular because it's like the whole island is the volcano and it erupts every 10 to 15 minutes. So,
every 10 to 15 minutes?
Yeah.
What?
So as we're speaking, it's erupting. Every 10, 15 minutes is going off.
And how is that not dangerous? How is it safe to be there?
So most of the time, it's very mildly explosive activity. So you cannot get to the top of the volcano unless you have a science permit. But you can still see it as a tourist from lower down, closer to the sea level. And yeah, so it's just really fascinating because that's the first one I saw erupting. And I remember the most fascinating thing was, of course, the amazing view of the volcano erupting, but also the thing that you don't see in the pictures is the noise. So the rumble as the magma and the gases are moving up towards the surface that comes before you see the volcano erupt is so incredible, very scary and very fascinating. And then boom, it goes.
And the material coming out of that volcano, even one that's not, posing great damage to the people who are visiting or living there, I mean, how close can you get to it? How close can you get to the magma or the ash that's coming out of that volcano, and what danger does that pose?
So that time when I saw Stromboli erupting, it was a very mild, very normal eruptive phase, like it is probably happening at the moment. And we were not far away, 100 meters away or something, and it was safe to do so. But sometimes this volcano comes through periods of heightened unrest and more dangerous eruptions, and so we need to be careful about that. In my case, the majority of the time I visit volcanoes after they're finished. Some of my colleagues have the very tough job of being there, in volcano observatories around the world, monitoring them and being there, of course, in a safe manner, but closer to the eruption itself. And, you just have to be careful. And if you are not a scientist, you just have to listen to whatever the scientists and the authorities are recommending to do.
This is definitely a time to follow directions.
Yes, absolutely.
What would have happened if you'd got too close to the lava there at Stromboli, if you'd, put your backpack in it or touch something? What would have happened? Volcanoes can erupt in different ways. So Stromboli is quite mild in that it makes very mild explosions, and it doesn't look too different to, say, what you see in Hawaii, which are kind of gentle lava flows. So lava flows run at more than 1,000 degrees Celsius. So you don't want to you don't want to put your backpack or your foot in it, but you can be not too far away from it and see it. But that's very different to when volcanoes erupt very explosively. And so that makes big clouds of gas, and it's hot ash and gas and, broken particles that can channel through valleys and travel really fast as a commercial airplane, and destruct everything they find on the way. So you really don't want to be in the way of one of those anywhere close or near, because they are really damaging and destructive. So the hazard potential of different volcanoes and different eruptions can be very different. And that has a lot to do with the type of magma that comes out. When the magma that comes out is more viscous, because it has more silica content, then the gases can build up a lot. And then when it erupts, it can explode a lot. It's a bit like if you open a shaken bottle of champagne, like it just explodes. Whereas if the magma is more runny, it's less viscous, like red wine, for example, then you can open the volcano and start erupting, and it will flow a lot nicer. Now, you don't want to be close to the very hot lava flow, but you can be close. Saying that, if the lava flows go on top of infrastructure, towns, it's completely horrendous as well. So when you talk about hazards and risk, it's not only about how much hazard the volcano can generate, but also what is at stake. Do drones let scientists get a better look at the top of a volcano, even one that's more active or more erupting more significantly than the one you were seeing at Stromboli?
Yes, so using drones is actually part of volcano monitoring at the moment. It's something that has boomed very recently, and they are very useful because they get where you're not able to get, either physically or because it's just unsafe to do so. So volcano monitoring has improved in leaps and bounds in the last few decades, in the last few years. And there's so many things that you can do today that we were not able to do before.
There are other parts of the world, Teresa, that your study of volcanoes has led you to, including the Canary Islands, this Spanish territory off the northwest coast of Africa. What kind of eruptions have you witnessed there?
So the most recent eruptions in the Canary Island, the most recent one in La Palma, happened just a few years ago in 2021. And that was very hard because that was one of those gentle lava flow type eruptions with a bit of tiny explosivity in the crater, but mostly lava flows. Were very well monitored. Everyone was evacuated in the regions where there could be damage. So nobody was harmed physically, but entire towns were wiped out. So psychologically, that's extremely hard. Because not only, you cannot come back to your house, you can't even see it. And you can't even maybe see the convenience store where you used to go to, or the cafe, or your life. So that's extremely hard. At the time, we were still in Australia with COVID restrictions. So I could not go to the field. But what happened is that my colleagues from Spain who were there on site on an almost daily basis were collecting samples of lava and send them to me in Brisbane. So I could analyze them in our lab at UQ with lasers that I used to measure chemistry of specific parts of the volcanic rocks that I'm interested in. And so that was very interesting in that we could see patterns of eruption evolution and eruption end that hopefully can be used in future eruption monitoring.
How long did that most recent eruption at La Palma last for?
3 months.
3 months?
Yeah.
And so what's the landscape like to go back to after experiencing 3 months of that kind of lava flow? What's the landscape look like?
It's a bit like a lunar landscape because it's all black rock that has covered everything. Sometimes you see the leftovers of house roofs, which is very sad. So, as the eruption progressed, it invaded more and more areas with houses and, crops and things. And people who were away from their houses were waiting to see when can we go home and when are things going to go back to normal. So often we look at, one of the things we work a lot on in my team and other teams around the world is trying to better forecast when volcanoes are going to start erupting. But another thing that is very important is to try to forecast how the eruption is going to evolve and when is it going to end for people who are, away from their homes to see when is this nightmare going to finish.
And once the volcano has stopped that eruption and the landscape is left, as you described, like this lunar landscape, is it safe to go back there and start farming again, build your home again? Or is it a sort of chemically tainted landscape?
So there are regions where you should not go and because they're unstable or because you could have degassing of certain gases that are bad for you. Most of the region that has been covered by the lava is not going to be used again in the near future. So people, as far as I know, they are trying to build houses and relocate people more permanently to other regions. But it's hard because you live in a volcanic island. So there are regions of the volcanic island that are more prone to have eruptions in the future. But it's hard to forecast exactly when the next one is going to be in islands like this, where the next eruption doesn't happen necessarily where the previous one took place. So, for example, in the case of La Palma in the Canary Islands, the previous eruption had taken place 50 years earlier, and it had taken place by the sea. So it didn't bother anyone. People could go and watch the show, and it just made the island bigger and, prettier because you see the new, the recent cone and the lava flows, and, you could see that as a tourist. You can still do.
podcast and broadcast. This is Conversations with Sarah Konoski. Find more conversations anytime on the ABC Listen app.
You say that scientists are getting better at monitoring volcanic activity and getting a sense of when a volcano is going to erupt. How do you do that, Teresa? What exactly are you paying attention to?
So different types of volcanologists do different things. So one of the key things we used, and this is done by geophysicists, is to measure earthquakes. So as this magma, which is molten rock, moves its way up to the surface, it pushes rocks apart. And as it does so, it can generate earthquakes. And those earthquakes can be measured at the surface, and you can know where from what depth they're coming, and if that depth is migrating up as the magma moves towards the surface. So that's a very good source of information of what's happening right now under the volcano, as long as you are monitoring the seismicity, the earthquakes. Another one is measuring if the ground is deforming up and down by a few millimeters or centimeters, not enough for us to feel, but we can measure that, for example, with satellite imagery. So if you detect that the ground is going up a bit, you could detect that there was magma coming in at depth that is pushing the ground up, and you could also see where, at what depth that is happening. And so that gives you another way of measuring what's happening right now under the volcano. And also you can measure if the volcano is degassing, is releasing volatiles, you could measure their composition.
So this is atmospheric changes as well?
That's right. So if there's a cloud of gas coming out of the crater, you could measure that chemistry. And if there's new magma coming in, it often changes as well to reflect what's happening beneath the volcano at a given time, real time. Now, that all gives you a picture of what could be happening under the surface, and it's done by amazing geophysicists and geochemists who have different skills to cope with all of these types of information. And then what I do and my team do is we try to build that doll's house view of how that particular volcano works inside, so that those who are measuring things in real time can say, okay, so, we get signals of magma movement at this depth, and we know from this doll's house view that this is particularly risky or normal or whatever. And, with what we do, which is take samples from previous eruptions and take them to the lab and interrogate them to get to know how the volcano works inside, you can help build interpretations of what the unrest signs mean in terms of, is a volcano going to erupt or not? When is it going to happen?
So there's different areas of specialty work together to illuminate each other. There's an idea that in the past meteorites caused volcanoes. Is that true? What's that theory?
When you have a massive impact on Earth, you make a hole. That's an impact crater. But if the impact is very big, even if it's small, but the bigger the size of the bolide and the speed, the bigger the impact will be. Then when that crater rebounds, then the rocks underneath may lose pressure, and that may lead to melting, and that may lead to volcanism. It's a bit like if you had a pond of water and you drop a drop of water on top, and then you make this hole in these rings, and then that kind of comes back up. And so that happens not only on the Earth, but also in many other planetary bodies.
So other planets don't have the tectonic plates that our planet has?
The Earth is very special in many ways, including plate tectonics,
There's evidence of volcanic activity here in Australia. Where are these extinct volcanoes? I mean, what are the landmarks that we see of that history here today?
We talked earlier about Hawaii and how it's reflecting a hotspot inside the Earth, making a line of volcanoes at the surface of the ocean. In Eastern Australia, it's a similar process where you have a hotspot inside the Earth that it doesn't move, it's stationary. And then Australia, over the last tens of millions of years, has moved to the north. And so because the hotspot stays still, stationary, and the Australian plate has moved quite fast actually to the north, you basically get a line of volcanoes, more or less, where all the volcanoes that the ones that are in the north and the younger volcanoes are the ones in the south. So the Glasshouse Mountains belong to that family, for example. And the reason you have these pointy shapes is because they are not the original volcano shape, but rather the top of the volcano has been eroded away because it's been, more than 20 million years of history of erosion. And what you get is the plug, the neck of the volcano, which is more resistant and eroded. And that's why you get these very nice shapes that you see in the Glasshouse Mountains.
And so as you're moving further south down the east coast of Australia, Teresa, the volcanoes are relatively younger, newer. So is this hotspot under Tasmania now, or where is it?
Well, the last volcano coming out of this hotspot is 6 million years old. So none of the volcanoes on the hotspot track are considered active or dormant. But there are other volcanoes, in addition to these ones, in South Australia and Victoria, that are considered dormant. And they're not linked to the hotspot. They have their own dynamics. And so the youngest of those erupted 5,000 years ago.
Which is not long in geological terms,
It's not
I
at
wouldn't
all.
think.
No.
So active and dormant, how scared should I be about a dormant volcano as opposed to an active one?
So the dormant volcano is not extinct. So it could go back to eruption. And the thing is that it is unlikely to erupt again in our lifetime, but it may erupt again. We just don't know exactly when.
What turns a volcano from active to dormant to extinct? Or how does extinction happen when it comes to a volcano?
Well, when what's fueling the volcano, the magma that's feeding it, the source of that is gone, then it's gone. Like we were talking about volcanoes that are generated when the plates move apart or when the plates get together or when there's a hotspot. So, for example, if the hotspot eventually becomes extinct, then that's it. Then you won't get another volcano on that track. You may get a different track. Or if you are in a situation where two tectonic plates move towards each other, like, for example, in South America, but then the shape of the subducting plate changes and, the volcanoes move inland or the other way, that region stops activity.
Is there a typical lifespan for a volcano?
It depends a lot. So, for example, in Eastern Australia, the northern volcanoes were active for a lot longer, say 7 million years, whereas the younger volcanoes in the south were only active for 1 to 3 million years. And we think that's linked to the fact that the fuel of these volcanoes was waning down as the track became younger.
I'd love to hear more about the work that you do in your lab at the University of Queensland, where you're looking at volcanic crystals. What are they and why are they important when it comes to understanding volcanoes?
Yes, so what we do is we collect rocks from volcanoes around the world and we kind of interrogate the pieces that make the rock separately. So one of the key pieces that make the rock are the crystals. So when the magma comes towards the surface and it cools down, it starts to form crystals as a result. And so these crystals are growing inside the volcano, in the guts of the volcano, in those magma chambers and magma reservoirs. And so as they grow, and they grow incrementally, they generate new layers, one after the other, and these layers can record what's happening in the magmatic reservoir as they grow. They are actually special crystal balls because you don't directly look into the future, but rather you look into the past as a key to the future activity. So you're looking at the past of how the volcano has worked in the past, what kind of depth it stored magma at, what type of processes triggered it to erupt. And then you use that information to then inform future forecasting on what may be expected when, earthquakes or ground deformation or gas monitoring indicate that something may be going on under the surface. They are tiny, like a lentil or a chickpea if you're very lucky.
You say you interrogate them. How does a scientist interrogate a volcanic crystal?
Yeah, so we use a range of methods, but one of the methods we use a lot is laser technology. So because these crystals are so tiny, we need microanalytical approaches. And so what we do is we use a laser similar to the ones used for eye surgery to remove a thin layer from the surface of the crystals on each of those layers of growth layers of the crystals. And so we transport that powder that we generate with a laser, it's called an aerosol, into an instrument that measures chemistry. It's called a mass spectrometer. And so with that, we can measure the chemical variations as the crystal grew, and we can actually visualize that with images of these crystals that show chemical variations with crystal growth. And that tells us, well, the crystal grew in terms of what depth, at what temperature, what type of magmatic liquid that carries them to the surface. So that's the matrix of the rock. And that, as much as the crystals tell us about what happens inside the volcano before it erupts, when we look at the liquid, what we are after are variations in that liquid as the eruption progresses, because then we can find indices that indicate us that the eruption is going to end, which is what happened at La Palma, that we found that 2 weeks before the eruption ended, there were changes in the chemistry of that liquid that we could maybe use in the future to try to better forecast the end of eruptions. So because the crystal grows incrementally, the final layer is the one that formed just before the eruption started. So that's the one that tells us, okay, the eruption started because of, for example, new magma coming in of this particular composition or at this particular depth, so that in the future we can try to track those type of processes as more indicative of eruption.
Those little chickpea-sized crystals can tell you all of that. Incredible. Do they look different? I mean, even to the naked eye or when you're studying them? And do they have different colours or different sort of shapes depending on where they come from and their age and all those other variables that you just described?
Yes, so they look different depending on the mineral that makes them. So depending on the magma composition, you can have different minerals. So for example, in very silica-poor lavas, like the ones in Hawaii or actually many of the Eastern Australian volcanoes, you often get black minerals that are very shiny, that are called pyroxene, or green ones that are called olivine, sometimes white ones that are called plagioclase. So you could actually go and look for them if you're hiking in a volcanic region, of which there are many in Eastern Australia, and try to see sparkles in the rocks. Those are the crystals. And you know they're going to be, about a lentil or a grain of salt in size, not very big. And so once you prepare those crystals for analysis, then you can, get to know all the secrets and about what happened inside the volcano, because they saw everything. And it's our job to try to get that information from them.
Another part of the world that you've travelled in your search for volcanoes, Teresa, is the Andes in Argentina. What's that landscape look like to just arrive there?
It's like another planet. Yeah, it's very high. And so we did field seasons in Chile and Argentina. And I went to the one in Chile when I was 3 months pregnant of my second child. I didn't make it to Argentina because I was in the 3rd trimester, not allowed. But it's just absolutely fascinating. It's really high. So, you are 3,000, 5,000 or more meters above sea level. And there are these massive plateaus where you see nothing in so many kilometers around you. Very harsh environment, very dry, extremely dry. I think it's the second driest place on Earth after Antarctica, and very windy and very rough environment, but very stunning. And you see these enormous, massive volcanoes all around you. And they are very interesting because these Andean volcanoes are linked to one of those processes of subduction where the Pacific plate goes underneath the western side of South America. And you get very viscous magmas that can generate very explosive eruptions. So we really want to understand them. But they are also interesting because they can accumulate metals that are critical for the energy transition. So for example, copper. An electric car uses more than 50 kilos of copper in one electric car. So we do have copper that we have found, but the demand for copper and other critical metals is increasing dramatically because of the change to green energies that can lead us to a more sustainable future. And so if we want to find more of those metals, we need to better understand the processes that concentrate them, and that can be in volcanoes, for example.
And how much is known about why this copper is generated by volcanoes or volcanic processes? Do you have a sense yet of scientists know why that happens?
There's a lot known about it because, of course, it's such an important metal, for everything we do. And so are many others like the rare earth elements you may have heard about, or lithium. And in the case of copper, the majority of the copper comes from these systems where you have subduction, so two tectonic plates meeting, and one subducting under the other, generating very viscous magmas that, if the right circumstances happen, may be able to actually accumulate copper in particular areas. But the ingredients to get the copper accumulated to levels that are economically important and can be extracted are not so well understood. And so the more we know about these processes, the better, because it is in our interest.
So it's not so much a matter of extracting the copper and other minerals where they exist around volcanoes, but how would we recreate that in other circumstances?
Exactly. How do we better understand why they accumulate, including in active systems, so that we can bring that knowledge to very old systems where we can actually find the copper that we need to source our electric and renewable energies.
You mentioned that you were pregnant while you were there. What did that mean for altitude sickness? I mean, you can already feel pretty nauseous when you're pregnant. Did it mean you felt even worse?
I was fine. I was fortunate. It just happens to some people that they get altitude sickness, and some of my colleagues did. But actually, there was another pregnant lady, a colleague of mine who works at University of Chile. And she was also similarly 3 months pregnant like me, and we were fine. So that was good.
Maybe it's like some protective force. Who knows? It seems there's more volcanic eruptions, or there's certainly in the news more. You know, they disrupt flights, and there's a lot of reporting on volcanoes. Are we in a period of geologically of particular activity, more so than in the recent past?
I get that question a lot, and it just reflects how connected the world is, and you know how fast the news cycle is around the world, because there are no more volcanoes now than before, and there are no more eruptions now than before. At any given time, you may have around 40 volcanoes erupting, and the ones that make the news are the ones where people are disturbed most of the time. So, of course, that makes sense. If you have a massive volcanic eruption in an uninhabited island in the middle of, I don't know, then nobody realizes, because maybe even nobody sees it. But if you have a volcanic eruption in a very populated area, you certainly hear about it. So, yeah, there's no more activity now than before, but we just know more about it.
How many people in the world live near an active volcano?
Yeah, so most volcanoes in the world are in the United States, in Japan, and Indonesia. And yeah, it's incredible. More than 800 million people live within 100 kilometers of an active volcano. So there are regions, like Indonesia is quite close to us, that are extremely active and extremely well monitored, and it's really populated.
Of all those active places, are there some that are in a way riskier to live in than others?
Absolutely. So, for example, in Central America and, you know, places where the resources are very low, the monitoring is less because there are not as many resources, but also the problem is that awareness is also lower. So you may remember there was a few years ago a big eruption in Fuego in Guatemala. It had a massive impact on the populations around, and there have been others like that. And it's a lot about public awareness of the risks of where they are living. So, for example, in the US, there are the most volcanoes that are active, but the monitoring is fabulous, and people who live in those areas are probably very well aware of how to react if something happens.
You've already visited so many volcanoes, Teresa, but do you have like a volcanic bucket list? Are there places, mountains that you'd really love to see, or parts of the world that you want to get to one day?
Yeah, so many places I haven't been to yet. I would like to go to Central America, which I haven't been to as of yet. And Japan, actually. I haven't been to Japan either. My next field trip planned, hopefully, will be somewhere in Southwest Pacific. And I'm really excited about it, but we are still preparing early in the preparation, but hopefully we'll get to Indonesia. And I'm looking forward to it so much.
Do you feel differently? Like when you're walking in parts of the world where you know there is this underground activity, do you think you've got a different awareness? You're alert in a different way than you would be wandering around suburban streets in Australia?
I guess I have an appreciation of the significance of the landscape, which is really nice. because I can't hold myself. If I'm hiking with friends, I would just talk about stuff. And then they are like, oh, that's so interesting. I said, I think so, but yeah.
It is so interesting, and thank you for sharing some of your incredible research with us on Conversations. Thank you for being my guest.
Thank you so much for having me.
Teresa Ubide was my guest on Conversations today, and Teresa is Associate Professor in Volcanology at the University of Queensland. This program was recorded on the lands of the Turrbal and Yagara peoples. The producer was Maggie Morris, and our executive producer is Carmel Rooney. I'm Sarah Konoski. Thanks for listening.
You've been listening to a podcast of Conversations with Sarah Konoski. For more Conversations interviews, head to the website abc.net.au/conversations.